And we're joined today by Dr. Robert Zubrin, an aerospace engineer, author, startup founder, and well-known advocate for the human exploration of Mars. Dr. Zubrin is the founder and president of Pioneer Astronautics, an aerospace R&D company developing new space access technologies, and founder of Pioneer Energy, developing new energy extraction technologies here on Earth. But he's perhaps best known as the founder of the Mars Society, a nonprofit that advocates for the human exploration and colonization of Mars. Dr. Zubrin holds a BA in mathematics from the University of Rochester, an MS in nuclear engineering, MS in aeronautics and astronautics, and a PhD in nuclear engineering from the University of Washington, and has authored over 200 published technical and non-technical papers, along with 7 books, and is the co-founder of Mars Direct, a critically acclaimed strategy for Martian exploration capable of reducing costs to 1/8 that previously estimated by NASA. Dr. Zubrin has won numerous awards, holds multiple patents, and has been featured in print publications ranging from The Economist, New York Times, Boston Globe, London Times, Washington Post, Fortune, Newsweek, and many more, along with televised appearances on the Discovery Channel, CNN, NPR, and the BBC. So, Robert, welcome. Sir, it is truly an honor to have you with me today. So, our topic today is mistakes in the Drake equation. I found this on the Centauri Dreams website, and it seems so timely given all the recent media focus on extraterrestrial life. So I wanted to turn back the clock a little bit and ask you, could you tell me what your initial inspiration was for that paper?
Well, my initial inspiration was looking at the Drake equation and seeing the flaws in it. And there's also an ideology behind it, which reflects the time it was written, which was circa 1960-61, which was a time at which people believed that the world was about to end due to nuclear war, that humanity was about to go extinct. And the polemic inherent in the Drake equation is our answer to the Fermi paradox is L is too short, that is the lifetime of civilizations. They become developed and soon they have nuclear weapons and then they destroy themselves, and that could happen to us. And this was very clearly Carl Sagan's ideology. He was very active in causes like nuclear disarmament. And that was the point they were trying to make. And you can agree or disagree with their concerns about nuclear war and the need for nuclear disarmament, but they created an equation in the course of doing that, which is simply invalid. Nuclear disarmament may be a fine thing, but the Drake equation is wrong.
Well, let me get into some definitions just for the audience in case they're not familiar with it. So basically, the Drake equation is a probabilistic argument that's used to estimate the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. So we don't know exactly how many of these civilizations exist, but the Drake equation basically gives us a best guess estimate based on what we know about the universe. So would it be fair to describe this as more or less kind of upper and lower bound brackets, right, on the number of civilizations that are using radio telescopes that are out there?
Well, that's what it purports to be.
Okay. Well, so Frank Drake created this in preparation for the first SETI conference, and that was held at the Green Bank Observatory back in 1961 with a focus on radio search, not a search for primordial or primitive life forms, quote unquote. So again, one of the stated constraints there, I think this is really important, is that we're only estimating a number of advanced civilizations, but it also really implies that we're only looking for civilizations that are openly communicating and doing so with radio waves, right?
Right. And it should be observed that having radios powerful enough to have any chance at all of being detected over interstellar distances, uh, well, it is not only a 20th century phenomenon, and maybe dates from around 1930. So in 1960, this reflects 30 years of human history. And only 15 years or so before we had nuclear weapons. We go from radio to nuclear weapons in 15 years, or if you want to be more generous about radio, in half a century. But in any case, a very short period of time relative to human history, let alone the Earth's history. And it's a blink of an eye. And so L is the time between when civilizations become advanced enough to have radio and when they destroy themselves. Okay. And this is the unstated intellectual foundation of it, is that a planet only gets one chance. Okay. And furthermore, it doesn't even acknowledge all the stars that actually exist in the Milky Way galaxy now. That is, if you look at the Drake equation, what it says is the rate of star formation today, okay, not the rate of star formation at the time of the galaxy's birth, but the rate of star formation today. And it compares that to the lifetime of a civilization. And then there's a bunch of other factors which basically work out to, if you got a star, what's the chance that it will create an active biosphere? So will it have planets? And will the planets be in the habitable zone? And then what's the probability that it will develop microbial life, and the microbial life will work out to become a flourishing biosphere filled with animals and plants and stuff. And then what is the chance that it will evolve intelligence from advanced animals? And then but then there's the time question. What is the chance that it's around now? Okay. So you got like 400 billion stars in the Milky Way galaxy. And if you take all these factors that, multiply by each other, the probability that there's planets, well, actually, we now know that actually most stars have planets. And they even suspected that in 1960, although I think they would have been surprised by how dominant planets are. But then that they'll be in the habitable zone and this, that, and the other thing. All those factors add up to 1 in 1,000. So now you got 400 million good planets. Okay. All right. But now, are they around now? What you basically do is multiply that by the factor of the lifetime of the planet by of the civilization divided by the lifetime of the star. And if you assume 10 stars are born each year, and there's 400 billion stars, that works out to the average life of a star being 40 billion years. And so let's say you took L as 40,000 years. Okay, that seems pretty long. I mean, that's the time that advanced Homo sapiens have inhabited most of the globe. 40,000 divided by 40 billion is 1 in a million. And then you got 400 million good planets. 1 in a million is 400 civilizations. Okay. And that's the kind of number that Drake comes out with. All right. But what if instead, okay, we'll take the same thing, 1 in 1,000 are good planets. Okay. But instead of the rate at which planets or stars are born, we take what is the time it takes if you have a flourishing biosphere, for it to create a civilization. Okay. That is, we have a fully developed biosphere, lots of animals, plants, and all this stuff. And then what's the time for that? Well, you get a much shorter time. In other words, after the KT disaster, for instance, within 4 million years, the biosphere is totally reestablished, albeit with different species. If humanity was to wreck civilization in a nuclear war, there's no question that in a few hundred years, human civilization would be back. Okay, if humanity was to drive itself to extinction with nuclear weapons or asteroid impact or some other such event, how long would it take for advanced mammals to recreate a intelligent species and therefore civilization? Well, 40 million years ago, there were no species on Earth more intelligent than dogs and rats and stuff like this. So we take 40 million years as the generation time, and then 40,000 is, then instead of that being 1 in a million, it's 1 in 1,000. And then instead of there being 400 civilizations in the galaxy, there'd be 400,000 civilizations in the galaxy. Okay, so that's the first difference. In other words, it's not the time it takes for a star to be born, which basically, if you say there's 10 stars being born in the Milky Way galaxy, then 1 out of 40 billion stars are being born each year, or put it this way, each 1 out of 40 billion stars is a newborn. And then they each get 1 chance. Here, if it's 40 million years, well, the Earth has been around 4 billion years. It probably has a comparable time left. It would have 100 chances at creating a civilization that will make it, because 100 times 40 million is 4 billion. Okay. And if you took a more optimistic estimate, if you think, gee, humanity wipes itself out, maybe 10 million years, the raccoons recreate a advanced species or something, or evolve into one, or some other primates do, or whatever. Then you get even larger. So instead of talking about hundreds of advanced civilizations in the galaxy right now, we need to be talking about hundreds of thousands or millions. So that's the first mistake in the Drake equation. And then the other mistake is that it has no acknowledgement of the idea that civilizations could spread.
Yeah. Well, let me back up a sec. And again, I mean, these ideas are why I absolutely just fell in love with your paper when I read it, because I mean, it multiplies the possibility of life. And I think it also implies a lot too. But so let me back up. There are 100 to 400 billion stars in the Milky Way galaxy. And so even if life is incredibly rare, it's unlikely that we're alone in terms of life. Back in 1959, Harvard University astronomer Professor Harlow Sharpley speculated there were potentially 100 million worlds with life, right? And that's primordial, non-advanced life. And then Frank Drake in 1961, I believe his estimates, I think, were 1,000 to 100 million planets, which is an incredible range, right? That may have civilizations. And he later revised that. I believe these are current estimates, down to a maximum of 15.6 million. But I've seen other estimates that have revised that much lower, right? And so a lot of this comes down to using those math figures. So I think you'd speculated just a moment ago, several 100,000, something along those lines.
Yeah, I would say 500,000 to 1 million civilizations in the Milky Way galaxy.
Okay. And again, those are communicative, right? So in 2016, Adam Frank and Woodruff Sullivan modified the Drake equation and calculated the odds were only 1 in 60 billion that the Earth is the only planet to host a technological species in the history of our galaxy. Based on those odds, do you think it's accurate to say that it's almost impossible that we're the only planet with life, and incredibly unlikely that we're the only planet with a technologically advanced civilization?
Sure. And I mean, look, what Lucretius said 2,000 years ago. Is it probable that in an entire field only one blade of grass should grow? He addressed this directly, and it's quite, look, the laws of the universe are the same on other planets as they are here. Okay. Life appears on Earth virtually as soon as it could. Okay, that is, we have biomarkers on Earth going back 3.7 billion years ago, which is practically immediately after the Earth was cool enough to have liquid water. So life appears on Earth as soon as it is habitable. Now, there's two possibilities. One, either the development of life from chemistry is such a lawful process that occurs with such high probability, like water freezing when the temperature is low enough, that just happens as a causal consequence, in which case life is plentiful throughout the universe. Or it means that, alternatively, there are spores, perhaps of bacteria, flying around in interstellar space. And as soon as any place becomes habitable, boom, they take root there and they start a biosphere. So, which of course is what we see if you leave, food out on the table. That in a very short amount of time, bacteria and then even insects will come and colonize it. Okay, so it's one of those two possibilities. Either life on Earth is indigenous, or it was spread here from elsewhere. Either it's indigenous or it's an immigrant phenomenon. And either one means that life is virtually everywhere. Okay. Now, furthermore, the entire process of evolution on Earth is one of development, from simpler forms to more complex forms. And the SETI pessimists make a point of saying, well, life does not develop monotonically to intelligence. Well, true. Life evolves in all promising directions. Okay. Intelligence is not the only favorable adaptation that life seeks out. It also develops wings. Flying is a good thing for an animal to be able to do, and many other traits that animals could have, they have developed. But certainly intelligence is one adaptive trait. And and furthermore, if we look at the history of the biosphere, you can see that the most intelligent animal on Earth today is more intelligent than the most intelligent animal 4 million years ago, which was more intelligent than the most intelligent animal 40 million years ago, which was more intelligent than the most intelligent animal 400 million years ago. So yes, life is exploring all possibilities, so it isn't on a single road up the hill to higher intelligence, but it's radiating in all promising directions, and one of them is intelligence. So life does develop intelligence, okay? And we would expect life to develop intelligence for exactly the same reason as we would expect life to develop mobility, okay? It's useful. And so if life's everywhere, it means intelligence is quite common, okay? And so, I think that, this idea that some people have, I had an argument with one SETI pessimist once where he said, well, intelligence is a singular characteristic of all the millions of species on Earth, only humans developed it. That's an incorrect point of view. Intelligence is shades of gray. Various animals have various degrees of intelligence. You know, and that in general has been increasing broadly within the animal kingdom over time. And so I see no reason to believe that life in other biospheres wouldn't find its own routes to developing higher intelligence.
Well, and one of the things about the Drake equation, it seems like it obfuscates this point about life being nearly ubiquitous, right? I mean, it's as you've said, it's likely to be everywhere, or at least in so many places that it provides humanity with a true inspiration to get out there and explore, you know? I mean, the Drake equation, and I think that the Fermi paradox is a corollary. I think that they are so focused on finding and communicating with intelligence that they tend to just cover the fact that, you know, as the human race begins to explore, we are likely to start finding life all around us, you know? And again, as you mentioned, perhaps in the most unlikely of places, right? I mean, Mars, which you've studied, is one where I know they're looking at salt brines, and that's just one example of these places where, you know, even if there isn't a complete, full, and rich biosphere, we may find life hanging on and doing so in very unique ways all over the solar system, potentially all over the galaxy. So for me, that's really exciting because it seems to indicate that there's a lot out there to find, even if it's not necessarily intelligent or communicating, right?
Right. But I believe, you want to know, that within 10 years, we will have discovered hundreds, at least, if not thousands, of biospheres. And we will do it with the Webb telescope and possibly other advanced telescopes, detecting oxygen in the spectrum of exoplanets. Okay, because you see, look, oxygen, well, a reasonably common element, not the most common, hydrogen vastly outnumbers it, but also not only hydrogen, but carbon, which is about as common as oxygen, and silicon and iron, which are comparable as well. Silicon, iron, aluminum, and hydrogen and carbon all react with oxygen. So there's a lot more dance partners out there for oxygen than there is oxygen in the universe, which means that free oxygen should be rare because these reactions are exothermic. They are highly favored by chemical equilibrium and chemical stability. And that is the reactions of oxygen with iron or carbon or hydrogen. Water does not spontaneously break down. It's very stable. Iron oxide is stable. Carbon dioxide is stable. Silicon dioxide, aluminum oxide, they're all very stable. So there's no way to have free oxygen unless somebody is making it. Okay, that is to say, life, which has the power to fight against chemical equilibrium through complex mechanisms, most notably, obviously, photosynthesis, creates free oxygen, where the life builds itself out of reduced compounds, releasing oxygen into the atmosphere. And that then creates the possibility of high energy organisms reacting biomass with oxygen to exploit energy. And so that's what we've got. Now, if we detect any planet with a serious oxygen atmosphere, I'm not talking about a few atoms. I'm talking about something like we have here. You got 20% of the atmosphere is oxygen. It doesn't have to be 20. It could be 5. It could be 10. Okay, but something like that. There's no way that can exist without life. And we're going to find it. Okay, now that won't tell us that there's a civilization there. After all, okay, by Drake's standards, okay, we've now had radio, call it a century, okay, 1920s to now, you know, out of 400 million years since we had a fully developed biosphere, including the oceans and the land. So that's a very tiny fraction. If astronomers on other stars detected the oxygen in our atmosphere during the Mesozoic, okay, they would have found, yeah, there's a biosphere there, but for some reason they're not signaling us, and that's because the dinosaurs didn't have radio. And neither did the amphibians or the mammals until 1920. That's another reason why I don't think anybody is signaling us with radio, because to use radio over interstellar distances requires very high power and very large dishes, and you could do it, but if you took the radio on the Mars Reconnaissance Orbiter X-band and you put it at TOS Ceti, instead of it being 6 megabits a second data rate, it would have a data rate of 6 microbits a second. Okay, you would have to increase its power 1 trillion times, from hundreds of watts to hundreds of terawatts, to maintain the current data rate. Or even, okay, let's live a little and we'll just go to 6 kilobits a second, which those of us like you and I have been around can remember when internet speeds were those kinds of speeds. Fine, you could do things. Okay, 6 kilobits a second would still require 100 gigawatts of power. Okay, you'd require amounts of power comparable to the American electric grid just to run a 6 kilobit a second transmitter from TOS Ceti to Earth. Now, of course, you make the dish bigger, you could get it down, but still gigawatts. Power, the kind of power we're using to power a city, would be needed to run even. So who's going to have the patience to do this for the past 400 million years, in which Earth would have shown itself to have a complete biosphere, and keep doing it even though there's no answer? Okay, nobody. So there's your Fermi paradox. Okay, they're not talking to us because they would have had to, keep talking for hundreds of millions of years with no answer, and have the patience for that to have any hope of still be talking to us.
Well, yeah, and I was also thinking that would be quite an incentive to pursue other types of communications, right? Like some kind of quantum communications, or something potentially more advanced than that, where it just
or spreading bacteria, genetic communication. Okay, now I wrote another paper which you may want to look up: interstellar communication using microbes. The idea is, what form of communication do we do with people that we don't know? And we don't send them the plans to starships. Okay, we send them messages. Well, most typically propaganda. And propaganda has the same root as propagate. Okay, it's a form of reproduction. Okay, because reproduction is adaptive. Giving away the plans to starships is not adaptive. Getting other people or civilizations to be like you, that is adaptive. So the Cold War, we had Radio Moscow, Radio Free Europe. Be like us. We have the way. The Gideons, they spread Bibles. Become a Christian. Be like us. These are efforts, and it's no coincidence that the two biggest religions in the world, Christianity and Islam, are both propagandizing religions. They both seek converts. Okay, Judaism is a much smaller operation because it doesn't actively seek converts. Okay, and a variety of other religions are small for that very same reason. And of course, many religions have gone extinct because of their inability to acquire converts. And the So a successful civilization or type of life seeks converse. So it is adaptive to spread your genes. So maybe spreading bacteria, carrying instructions that will lead to organisms like you, is adaptive in the broadest sense, or life forms that want to spread. That is an adaptive trait for them. And so maybe the answer to the Fermi paradox is we are here.
Yeah. Well, there are so many big ideas. Again, thank you so much for joining me today. And so one of the other aspects you touched on this briefly was advanced civilizations are going to be better not only at sustaining themselves, but at reproducing themselves, colonizing other worlds, right? So you were just talking about bacteria. I mean, potentially there could be you did calculations for speed of reproduction, I guess. And I'm not going to get into those, but I think we were talking about spacecraft there, right? Like actual colonies,
Right.
outposts, and things. And what's interesting was you were saying that like an intelligent species could reasonably include a settlement zone 62 and a half light years in diameter, encompassing up to 3,000 stars. So basically, life spreads out, right? And again, that's something that we see on every level, from bacterial colonies to human societies. Life spreads, it reproduces itself, it grows, and that seems to be a natural condition of it.
Sure. Now, in the paper, I do discuss this. Now, it's possible with like fusion rockets, things that we can envision, if not quite built today, but nevertheless, it's within our physics, to get spacecraft that move at up to 10% the speed of light, which would get you to Alpha Centauri in 40 years. But the rate at which a civilization spreads would be considerably slower than that. In other words, if you look at the rate at which, say, Western civilization spread across the globe, even after it had long distance sailing ships that could travel the globe, okay, say from 1500, traveling at 3 knots, the speed of a sailboat or a soldier on a forced march, uh, you know, uh, in a year you could travel all around the world. But you know, they reached America, but they only started colonizing it, and it took basically 300 years after the Pilgrims land that North America is substantially settled by people of European descent. So instead of 1 year, so it's 1/300th the speed at which you could simply travel. Okay, so rather than a speed of like 5% the speed of light, maybe the speed is more like 5% of 1%. That is the speed of colonization. So if we take, say, L equals 50,000 years, and you're traveling at 1% the speed of light. Well, the 1% be high, 0.1% the speed of light. That means that in 50,000 years, you could travel 50 light years. Okay. Now, there's a fair number of stars within 50 light years. I think you quoted a number from my paper. It's tens of thousands. So that's a substantial little interstellar empire. But still, 50 light years, that would increase the number of civilizations, say, by a factor of 10,000, number of civilized planets, 10,000 per civilization instead of 1 per civilization. So now if we're talking Milky Way galaxy, 400 billion stars, and if there's 1 million civilization times 10,000, that'd be 10 billion. That would be 1 in 40 stars has an outpost of a civilization. That
Yeah.
would still mean that the vast majority are unsettled, and that the chance that we would have encountered aliens are low, especially around here, where we live. We don't live in the center of the galaxy where most of the stars are. We're living out in the semi-rural areas, not quite at the rim, but we're kind of on the edge of where the suburbs have some farms still in them, and we're out past the well-groomed suburbs. We're semi-rural here, and that's the part of the galaxy where we live. We're certainly not in the big city, and we're not even in the fashionable suburbs where people commute into the big city. We're kind of out at the edge of the suburbs where you can still see some horses on some people's property and some stuff like that. That's where we are. So we're in not the least densely settled part of the galaxy, but certainly not in one of the concentrations.
Well, I wondered about that though. The closer you get to the center of the galaxy, the more radiation you have, right? It seems like that might be inhospitable to life, at least as we know it.
Well, what do you mean by radiation? I mean, we have on this planet, okay, we have an atmosphere above us, which is equivalent to 10 meters of water in mass. It's terrific shielding. So, I mean, yeah, there's a black hole at the very center of the galaxy, but if we move out 1,000 light years from the center, you're pretty far away from that. And here we are, we're 30,000 light years out. So yeah, okay, you don't want to be in the exact center, then you'd be in a black hole, but still, you could be in the galactic metropolis and have stars a lot closer to you, which means not only more stars, but the chance of travel from star to star is much easier, because instead of a characteristic distance being 6 light years, it might be half a light or a tenth of a light. And also much more frequent, closer encounters. Earth, a star comes within our Oort cloud about every 20 million years. That is, right now, the closest star is Alpha Centauri, but every 20 million years or so, on average, a star comes within a tenth of a light year of our sun, and that actually probably precipitates a cometary bombardment as Oort cloud objects are precipitated. And we're also, of course, traveling through their Oort cloud. So we may be hit at that time not only by objects from our Oort cloud, but from their Oort cloud. There can actually be an exchange of material. It's kind of like during the age of sailing ships. And of course, the sailing warships had cannons. And those cannons only had a reach of a few hundred yards. How could they ever hit each other sailing they had global range. They were wandering over the whole earth. How did they ever manage to hit each other? Well, it's because they only shot their cannons when they were close to each other. They just shoot their cannons as they traveled around. So the stars are probably exchanging materials exactly when they're close to each other. And then we each get a broadside.
Okay. And so that might explain panspermia as well, right?
Yes. Yes.
Okay.
Interstellar span, sure.
Yeah. Because if those bacteria or if those microorganisms are, again, if they're spread out in the solar system, they would probably stay inside the solar system, maybe in the Oort cloud where they would be frozen and preserved, potentially in comets, right? As has been speculated in the past. And if there is some kind of an interstellar exchange, it would happen when these solar systems basically come close enough to exchange debris, I guess. Yeah, well, I mean, so you've outlined two big mistakes in the Drake equation, right? And I mean, again, this multiplies the amount of life that's out there. Now, one of the third things that I wouldn't call it an outright mistake, but one of the things I've wondered about is, again, going to Mars. We are exploring Mars as well as most of the other planets in the solar system in one way or another with robotic probes, right? The spacecraft, rovers, landers. I mean, you name it. And we start with machines. We start with robots. Those aren't highly communicative, right? They're communicating back to Earth, but they're not broadcasting messages out there. But
No.
it seems like a lot of the SETI approach to things, and I understand why, but it seems like a lot of their approach to things is looking for these big biologically based centers of life, I guess. So one of the other things that I'd kind of wondered was, should we be looking more for technology rather than looking for biology?
Well, I agree with that point, because communication systems use conventions. And for example, at the time when Drake wrote his paper, um, we were using L-band to communicate with satellites. And so there were dishes that were meant to receive L-band. And he said, this is the ideal frequency for space communication. Well, it's already obsolete. Nobody uses L-band anymore. And X-band, a much higher frequency, is um, the coin of the realm, but people are moving to Ka band, which will be even higher frequency, and laser communications, much higher frequency. And, so looking for L band is like looking for gas lights. It's a feature of a civilization that is, it's a transitory technology, something that was around for a while and got superseded. And the stuff we have now is being superseded. On the other hand, certain activities of civilizations that are high energy activities, the are intrinsically more detectable. You don't need to know in other words, I wrote a paper once on detecting extraterrestrials by the spectral signature of interstellar spacecraft, because interstellar travel requires very high energy systems. In another paper, I wrote artificial singularities as a way of detecting extraterrestrial civilization. And here I'm talking about something that is beyond interstellar spacecraft. Here I'm talking about creating artificial suns by creating black holes. And there's a theoretical possibility. It's considerably more difficult technological feat than creating a fusion rocket. But, where will humans be not 100 years from now when we might have fusion rockets, but 100,000 years from now, in terms of our technology? You create artificial suns, and there's a lot of utility to artificial suns. If we had an artificial sun, we could put it in orbit around Neptune, and we'd have a whole planet that'd be warm enough for settlement. I mean, the most of the universe, the large majority of the universe is much too cold. The large majority of the universe is very far away from any star, much too far away to be warmed by a star. If you could create your own stars, well, you could really have a good time. And the you could settle vast reaches of space that are currently uninhabitable. So what would artificial stars look like? And actually, if you want to know, in that paper, I go through what an artificial star would look like and how we might even be able to detect them right now with Hubble, and distinguish them, because it would have the same color spectrum as like a G or a K star, but be much too small. And so in order to even appear on a photographic plate as one of these undistinguished little dots that there's thousands of them in the background of any astronomical plate, it would have to be much closer than a K star in other words, most of those little dots in the background of the plate are hundreds of light years away at least. this would have to be closer than 50 light years in order to even appear on the plate as a dim little object. But unlike the rest of them, it would show parallax. That is, when the Earth moves from one side of the sun to the other, if an object is close enough to us, it actually moves in its apparent position in the sky. And we did a computerized study of photographic plates and looked at all these dim little objects and see if any of these little dim objects move with parallax. You could be detecting an artificial star.
Robert, it has been a true pleasure and honor having you on. Let me close by
we did a computerized study of photographic plates and looked at all these dim little objects and see if any of these little dim objects move with parallax. You could be detecting an artificial star.
Robert, it has been a true pleasure and honor having you on. Let me close by asking what comes next in your own work? And given the rapid progress of research in science, technology, and astronomy, do you see more accurate versions of formulas like the Drake equation in the near future?
Well, perhaps, because as I said, I believe that the people studying exoplanets will soon devise ways to detect oxygen in the atmospheres of exoplanets. And once that's done, we're going to start, I believe, to see it in a lot of exoplanets. For the longest time, like when I was a kid or in college even, no one had ever found any exoplanets. And it was a respectable position. And I still have some of my childhood astronomy textbooks that say there's two theories about the origin of planets. One of them is the nebular thing, where at the same time the star is formed, a bunch of planets are formed around it. That would mean that planets are highly common. The other is that planets only form when stars collide. And that's an extremely rare thing, in which case there might be no other planets. Okay. And now, of course, in the science fiction world, it was immediately assumed that there were other planets. Okay, because it's necessary for science fiction that there be a lot of other planets. Okay. But among the quote unquote serious scientists, it has yet to be proven that there are other planets until the 1990s, when the first exoplanet was discovered. And then a few more were discovered using that particular technique. And then once they flew the Kepler telescope, then thousands of exoplanets were discovered. Okay, so now they have additional ways. Now we know how to find exoplanets with finding thousands and thousands of them. And as soon as we develop the right technique for discovering oxygen in the atmosphere of an exoplanet, I believe we'll discover thousands of planets. In other words, first there'll be one, it'll be argued about, contested, and finally settled, and then there'll be 4, and then there'll be 28, and then there'll be 300, and then there'll be 35,000. And that's what it's going to be. And I think we're going to live to see that. And that will make it clear that biospheres are very common in the universe. But detecting civilizations, I think, requires detecting artifacts. And I think looking for high energy artifacts is the best way to go.
On that note, let me thank you again so much for